Start volunteering.
Yes, let's start. Okay, so it's our pleasure to have Antoine Browaeys speaking today, and I'm sure Antoine basically needs no introduction here at Harvard or at ITAMP, but I'll do it nonetheless. So Antoine studied in Paris and did his PhD with Alain Aspect at the Institut Optical in Paris, and then in 2000 he moved to the US to enlist to do a postdoc in laser cooling and trapping, but then returned to France to become a researcher at the French National Center for Scientific Research, CNRS. And then there, and after that, started building his own group at the Institut Optical again. So, and from that time, of course, there's been lots of beautiful physics and pioneering work with individually trapped Rydberg atoms, and I'm sure many of us have seen these beautiful pictures also. And yes, so his work has earned him a couple of prizes, and I'll just name the Aimé Cochon Prize, the prize from the French Physical Society, and the prize La Recherche also in 2014. So today, we'll hear more about trapped atoms and many-body physics with arrays of individual atoms and optical dipoles. Thanks for being here, and the screen is yours.
Thank you very much, Valentin. So you can hear me well, so that's fine? Yeah, okay. So it's a real pleasure for me to be in Harvard, so to speak, and to have had the chance to talk to many of you actually before this talk. I think it's very nice that we can still have these interactions, even if it's online and a bit less friendly. It's still super nice to be able to catch up on the science in this complicated period. So indeed, what I would like to do, and so the problem is always that I may disappoint some people by not going too much into detail, but I will give you an overview of works we've been doing essentially this year, despite the fact we've been locked out of the lab for 2 months, but we still managed to make some progress. So around this many-body physics, using arrays of individual Rydberg atoms, that should be about the first half of the talk. And then optical dipoles as well, to vary a bit the subject, so to talk about 2 projects we have. And so picture of, so just one thing I want to mention, I think I will do a break around I'll have the talk, so if you want to ask questions at this time, I think it will kind of be a natural moment to do that, but of course feel free to ask questions at any time if you want, but I will just pause at after the talk. So this is our team pre-confinement, actually. The team has shrunk slightly. And so essentially, the work I will be presenting is the work from Pascal with the PhD student, together with Daniel and Anna, or the postdoc, Kai, PhD student as well, and under the supervision of Thierry, who is a permanent staff member in our group that many of you know. And we have another project that I will discuss with the PhD student Antoine and Giovanni, who is postdoc, and under the supervision of Igor, who is also a permanent staff member in our group. As you will see, we have several collaborations with theorists. So we work for what I'm going to report today with Andreas Leuschli, and we also have an active collaboration with Hans-Peter Büchler on a topic that I'm not going to touch upon because we haven't done much progress this year on this. On the other project, we also have some collaboration with Darek Chang and Ana Asenro Garcia in New York, and also with experimentalists in Durham. I just seized the opportunity of being here, so to speak, to just advertise the fact that we are looking also for postdocs. So if you are interested, please do not hesitate to contact me. I mean, times are not ideal for visits, obviously, but I'm sure we can arrange ways around that. Okay, so as you know, and this is not new because many people, including in Harvard, are looking at that. What we do is to study many-body physics using a synthetic matter, which is to say matter that you can assemble atom by atom. And the goal, obviously, is to understand some open questions in many-body physics, trying to understand how ensembles of interacting quantum particles work. And essentially, in our group, we do that with 2 platforms that we have developed over the years. So first, there are these tunable arrays of individual Rydberg atoms. So essentially there, we can arrange the atoms in various geometries, very well localized. The typical distance is about 10 micrometers, and we need to excite them to Rydberg states for them to interact. The second experiment or line of research we have is about inducing the interactions between the atoms with light. And in this case, the distance that you need to reach for the atoms to interact is more on the scale of the wavelength of light. So it has some experimental consequence that I will show you later. And what is also common to those two setups is that essentially they implement kind of a Drosophila of many-body physics, which are spin models for particles or spin 1/2 placed and pinned on a lattice. So essentially, the two models that we implement with those platforms are the Ising model, which is the sigma z type of model, or the XY model, sigma plus, sigma minus, which corresponds to the exchange of excitation. And I will illustrate that in the two different parts of the talk. So this is what I'm going to cover. So for about 20 minutes, I will kind of update you, so to speak, about what we do on our Rydberg platform, trying to study quantum magnetism using the transverse field Ising model that we implement with these Rydberg arrays. I will show you the progress that we've made. And then I will switch to another kind of interaction, the second one that I've discussed, which is the resonant dipole interaction induced by light. And we will see how you can create small atomic chain that scatters light in a collective way, and how we can also demonstrate subradiance on the release of subradiant excitations in this system. So let me start with the quantum magnetism. So this is work we do with Andreas Leuchli, together with his student, Michael Schuler, Thomas Lang, and Alex Eberharter. In Innsbruck. And the platform we use in order to do that, to implement this quantum Ising model, I mean, many of you know it. So this is our arrays of tweezers. So a tweezer, this is a laser beam which is tightly focused, typical size about a micrometer. And in this dipole trap created by light, we can place one and only one atom. That was work pioneered by Philippe Grangier 20 years ago now. And the nice thing is that you can send resonant light onto the system. The atoms will fluoresce, and you collect the light on a CCD camera. Now, obviously, if you want to have many atoms, so you need a way to multiply the number of traps. So there are ways to do that in Harvard, for example, using 2D AODs, what we can also, or SLM. So what we use here are spatial light modulators, which is to say arrays of liquid crystal. The trapping laser impinges on it. A phase is written, which you can see here, for example, and what you have in the focal plane is the Fourier transform of the phase factor you've imprinted. And in this way, there is a relation, and you can create any arbitrary geometry. And kind of the largest array that we can create those days, and it's essentially limited by laser power, the usual problem, we can reach now arrays of about 700 atoms. So be careful here, this is an average fluorescence of the atom. So each of the bright dot is a single atom, but we average so that all the traps look filled at the same time. I mean, if you do not average, you just take a snapshot, you will have only 1/2 of the atoms filled. Nevertheless, it shows that the system is able to handle such large number of atoms. And for us, it corresponded to an improvement by a factor 10 in the number of atoms we could handle. So we've also improved the way, and I'm not going to give too many details, but essentially we have a way when the array is not fully filled to move the atoms around to assemble one by one the structure. And this is what we can now almost routinely do, actually, and to handle about 200 atoms. You can push slightly further, but then we've got holes. So you can have this kind of 1D snake, if you wish, of 210 atoms. 2D arrays, 14 by 14, these triangular geometries, and something we've done as well, we've improved the algorithm to sort the atoms in the array in order to be able to prepare any random arrays. And so this is something for which you can find details on the archive early this week. And this is an example of a pixelized version of the Mona Lisa, just to show the kind of control we've got over the system. All right. So as I said, so we start from that. This is the platform, arrays of individual atoms. Typical separations between the atoms is on the order of a few micrometers, and therefore the atoms do not interact when they are in the ground state. So we need to make them interact. And so we do that by ideas, suggested actually in Harvard and ITAMP, to excite the atoms to Rydberg atoms. So that they will develop a long lifetime, and also start to develop large dipole moment in such a way that the atoms may interact very strongly, even at micrometer distance. very strongly, meaning that if you place the atoms at about 10 micrometer distance, then the strength is in the order of a megahertz, which leads to a dynamics time scale driven by the interaction, which is sub-microseconds. All right. So now I come to what we study with that. So we study the Ising model, the quantum Ising model, or which is known as well as a transverse field Ising model. And so in order to do that, we use the most natural interactions that you encounter between atoms, which is the van der Waals interaction. So essentially the idea here is that if you place two atoms in the same Rydberg state, this doubly excited state is shifted in energy by a C6 over R6 amount, and the C6 is a very widely varying power of the principal quantum number, which makes the interaction switchable. If you want to describe this diagonal interaction by an Hamiltonian, you write that it has this form between a pair of atoms. So essentially, this is the strength of the interaction times the occupation number of the atoms in the Rydberg state. So that's the first part. So we've got the Ising interaction, so to speak, the spin-spin interaction. But of course, you also want to have the transverse field. And the transverse field is done by applying lasers on the array to couple the states, which would be ground state and Rydberg state. Those lasers, so we've implemented actually the scheme from Harvard that demonstrated high fidelity, which is 421 laser followed by a 1013. Which are detuned with respect to an intermediate transition. But in any case, for all the details, for what I'm going to discuss now, you can totally ignore the details of this and essentially just say, well, ground state is spin down, Rydberg state, very well-defined Rydberg state is spin up, and we couple that with this coupling strength omega. So using this laser system now, we can really have a very nice coherent oscillation. So this is the kind of Rabi oscillation between those two states that we have now with this new system. And for us, it was a big improvement because we could increase the coherence time by about a factor 80, and the contrast is much larger, as you can see on this high resolution oscillation in the first period. So really, it really means that the control we gain over the system in terms of size of atoms, but also of coherence, has improved a lot thanks to the implementation of these new experimental tools. Okay, as you know, when you have you combine those two things, so the driving by a laser and the spin-spin interaction, you have this quantum Ising-like model, which shows up as a term which is the driving by the laser. The detuning is the equivalent of either a chemical potential or longitudinal field. And this is a spin-spin interaction term, which is the van der Waals interaction. Okay, and experimentally, obviously, if you know, you can vary the geometry of the arrays, you can vary the C6, you can vary the laser power, and in such a way, you can bridge the gap between fully interacting to non-interacting regime. So what I'm going to illustrate now is going to be the only example I show you is the demonstration or the trying to prepare antiferromagnetic ordering on a square and to explore the phase diagram of a square array, implementing once again this kind of Drosophila of many-body physics, which is the 2D transverse field Ising model. So the kind of thing we're starting from is an array, a typical spacing A, and we consider only nearest neighbor interaction, and we work in a regime where the nearest neighbor interaction is on the order of the strength of the transverse field, which is to say the Rabi frequency of the laser. So it means that essentially the atoms within this blue sphere here can get excited, and if a nearby atom cannot get excited. So now, of course, if you want to add many Rydberg atoms, you end up in this staggered configuration, which is reminiscent of an AL state. So the blockade due to the interaction leads to an antiferromagnetic ordering, which can be either this one or the other one, which is this inverted configuration. So of course, the thing is a bit more complicated. You've got a full phase diagram, and even this one is very schematic. So you have a quantum phase transition represented by this dome here, which separate a paramagnetic phase and an antiferromagnetic phase when you plot it as a function of omega and delta. So this is all quantum, and there is no temperature in this business. It's all the quantum field model with the quantum fluctuation being the Rabi frequency. So I should say that, as I said, this is an extremely schematic phase diagram, and actually there are, if you go beyond the nearest neighbor phase transition, the phase diagram is much more complicated, and actually there are some very nice work from early this year from Harvard, Misha and his team, and Sajdev Subradiance and his team, who actually looked at all the possible phases that you have on this square. So for us, we're going to stay away from those phases. I mean, in this diagram, essentially, they would correspond to phases confined around here, around the critical line, and we were going more to explore the central part of the phase diagram, if you wish. So if you want to do that, the idea is to start from the atoms all in the ground state, in a sense, and to tune dynamically the atoms and drive them through the phase diagram and see what's the magnetization as you move across this. Ideally, you would like to do that adiabatically. With the kind of system size we have, it becomes much harder to be fully adiabatic, but nonetheless, we can drive the system almost towards perfect antiferrometric ordering, as I will show you. All right, so let's try to do that. So we start from an initial array, which is a perfect array. So we can post-select on the arrays that are that have no holes, no defect. So this is the example of a 10 by 10 array. You vary you sweep the frequency and the detuning in a way I will show you later. And you take a snapshot when at the end of the ramp, when you are back onto this classical line. And so when you end up with this kind of image, where essentially you have the feeling that there are missing atoms with respect to the initial condition, the initial array. And indeed, this is what we have, because a missing atom for us corresponds to the detection of a Rydberg atom. And so our detection method is destructive, which is unfortunate, but this is the way it is for the moment. And therefore, you have this staggered configuration. I mean, if I show you it this way, you have the feeling that it works all the time. As a matter of fact, it's clearly not the case. It's indeed a perfect antiferrometric ordering, but it doesn't occur very frequently. And so if you plot, let's say for the 8 by 8 array, the probability to obtain a staggered configuration corresponding to the nail ground state or the opposite one, we end up with this state histogram. So here what you have, in a sense, all the 2 to the power 64 states that could be accessed in principle with our method. And we see that 2 prominent peaks appear that correspond with a very high probability, so to speak, because it's only 3%, to the 2 nail states. Okay. So indeed, it means that despite all the defect, non-adiabaticity, and so on, you can still prepare with a reasonable probability and have those 2 states that stand out of a huge amount of states. So now what we can also measure, obviously, are correlations. So now what you take many snapshots of many realizations of the experiments, and you calculate from them the correlation function, which is to say the probability to have one atom up when you have another one down, and vice versa. And so what we see here is this kind of checkerboard configuration where you have the alternance of red and blue, which corresponds to either, so red is correlated, blue is anti-correlated. So we do see the appearance of a correlated order, as we already know here, but now it's average over many realizations. And from there, you can extract, for example, the correlation length, although for finite size system, it's not necessarily a super well-defined quantity, but anyway, the correlation, they extend over essentially the system size, so about 9 sites across the array, indicating that indeed, even though it's not perfect antiferromagnet that we prepare each time, we are not too far from it, otherwise the correlations would be much smaller. So the largest correlations that we've been able to prepare are on a 14 by 14, so don't be misled by the fact that this is not exactly the same scale, but I mean, this is the 14 by 14 arrays with a positive and negative configuration. All right, so the thing that we've been doing over the last few months, actually, and that was pretty challenging with the help of the theorists, is to benchmark the dynamics across and while we drive the system across the phase diagram. So the reason why it's challenging is because now we are using a large number of atoms, and also because we need to calibrate very carefully everything on the experiment, detection errors, the exact ramp that we send to the atoms, all little imperfection on the exact position of the atoms in their tweezer, and so on. And so we send those ramps on all those imperfections to the theorist, and we measure many quantities that we can compare to the theory. So the quantity that I will show you, but there are others that we've also looked at, is the most obvious one, so to speak, because this is the order parameter, and that's the staggered magnetization. So the staggered magnetization corresponds to essentially the difference in occupation or in number of atoms between a site, a sublattice A and sublattice B, because for this square array, it's a bipartite symmetry that you have. So this is the result of the comparison between the experiment and the data for this dynamics. So essentially, we vary across the phase diagram. So while we run down there, actually, or even before, it doesn't matter. But during this sequence, we decide at which time we switch off, measure the magnetization, and run an MPS calculation. So we've benchmarked that for a 6x6 array. And you do see that already for these 36 atoms, there is a very good agreement between the data and the MPS calculation, be it ideal or taking into account all the imperfections that I was mentioning. So the finite size of the beam, the fluctuations shot to shot of the interparticle distance, which leads to the interactions between the atoms slightly fluctuating, the real ramps and all these detection errors. For the 10 by 10, we've done the same kind of MPS analysis, so the colleagues in Innsbruck. And so this is a comparison between the data and the black line, which is the average of the many trajectories of the same MPS calculation. And you do see as well that the agreement is reasonable. But it's, if you compare that to what would be the case with no imperfection, clearly we are far from that. So we do understand the imperfections. Putting them in the calculation is does lead to good agreement between theory and experiment, but clearly it means that there is room for improvement in the experiment in order to kind of get rid of all of them. And it's not a straightforward work, but it's kind of a roadmap for us. The thing I want to emphasize is that the MPS calculation that the colleagues in Innsbruck do, so this is MPS that to reach a result which is meaningful. So it's matrix product state. And for those of you who don't know, so I'm not really expert of this method, but essentially this is a tensor network method that allows you to account for entanglement in the system up to some orders. And essentially for this kind of curve that they obtained, it was 5 days of calculations over clusters in Innsbruck. So it starts to be a demanding calculation, while the experiment essentially has been taking over half an afternoon. So you see, this machine now do challenge the theory. Okay, so that's essential. So we've done lots of other work in this direction. So we're looking at the quantum phase transition between the paramagnetic and the antiferromagnetic phase. And we're also exploring at the moment the case of a triangle array. I will not report any results. We've seen different phases and things, but that would be almost a full talk. But what I suggest is that I can kind of stop here for the moment and have a short discussion with you. If you have questions that you would like to discuss, we can do it now, and then I'll move to the second part of the talk.
I have a question, Antoine.
Ready? Yeah. Mm-hmm.
Could you go back to the previous slide?
Yep. Oops. Sorry. If I can.
What are these different gray lines with these different like positional? Are you sampling from some? What are the different gray lines?
That's exactly that. So essentially, the black line is the average over many of these realizations. So for this, if I remember correctly, they run 20 of those trajectories. Each time they sample the Uij, the omega I, the delta I. So omega I and delta I actually they include the shot-to-shot variation due to the lasers in intensity, which leads to a delta I, a detuning that varies because of the what do you call it? The light shift in the two-photon transition. And the Uij, they come from the fact that the atoms, despite being cold and reasonably close to the ground state of the tweezer, they are not infinitely closed, and I mean, they're infinitely at the bottom of the ground state, so they do fluctuate from shot to shot. And the van der Waals interaction is particularly annoying from this respect, because I mean, when you kind of have the order of magnitude of the fluctuation, it's delta R over R times U times 6 because of the power law. So that kind of, even if you have only 1% fluctuation, it leads to a 10% fluctuation almost in the Uij from shot to shot. So all this is taken into account in this MPS.
Antoine,
do you have an idea if any? Oh, sorry. Go ahead, Sipper.
Go for it, Tiger.
Do you have an idea if any one of these particular fluctuations is the dominant contribution compared to the
yes,
ideal?
I do have an idea, and essentially they all contribute, unfortunately, which is to say we will have to work hard to remove them one by one. The detection error for sure has an effect. So I haven't written what the values are here. So in terms of the false positive and false negative, this corresponds to 0.4% for the smallest one and about 2% for the other one. So we are not as good as you guys are for the detection error and the detection of a Rydberg. So this is also something we are working on, trying to improve that, because for sure it's going to improve. But unfortunately, as I said, it's not. It's an important source of error, but I wouldn't say it's the widely dominant one. So we have to work on all of them.
Got it. Thanks.
I was wondering, in the experimental data, when you're doing this benchmark, would you say on average things look like this? Or there are cases where the experiment horribly goes wrong, and those are like easily detectable, and you can like post-select for not including that?
Okay, so that's an excellent question. And so of course I wouldn't swear for all the parameters of everything, but we looked at that reasonably carefully, and we didn't look at any wild event. So in a sense, if I had to plot the variance, including all the events, we wouldn't have widely off events. Okay. I don't have the figure here, but essentially what we looked at when we do this square thing, we plot the full histogram of the clusters that we have. So essentially you can define the size of the cluster state. You can define the size of the largest antiferromagnetic cluster you have on a single realization. Okay, you take the largest cluster that you find in your image and you plot this distribution. And so this distribution is essentially peaked, and once again, it has to depend exactly on the experiment. But basically, we have more than 30% of the events for which you have less than 10 defects in the antiferromagnetic ordering. And the distribution is actually, doesn't go all the way down to 0. So essentially, the largest cluster is about the total number of atoms we have. Most 30% of the events are within 10 imperfections, and we have a tail, but the tail doesn't expand all the way down to 0. So we don't have events for which it widely leads to something which obviously went wrong. So we do not need to post-select. That's what I'm saying. It was Harry who asked the question, no, Cesar?
That was a great explanation. Thank you.
Okay.
Antoine, I have a question. Can the MPS code identify the quantum critical point and compare versus your experimental data? And then related to that question, I know you've done quenches at different quench rates, and I think I would expect that for slower quenches, there's less time evolution after you reach the quantum critical point, or you saturate your correlations or your order parameters sooner. So can you comment on both of those questions?
Yes, so for the second question, essentially, so we've tried that. We try to vary a bit the slope, trying to improve, for example, the correlation length that we have. And so what we find is that if we try to be slower in order to have less time evolution after going through the tip of the dome, then we start to have problems with the decoherence, because I mean, then the pulse becomes, the sequence becomes too long, and we start to have a little bit of spontaneous emission, a bit more detection error of the Rydbergs. And so unfortunately, it's kind of a trade-off that we've reached. You cannot be widely slower, because then you have other sources of imperfection that arrive and that are not included in the MPS. And like decoherence is very hard to include in an MPS, phase noise of the laser, for example. So yeah, so that's more or less that. And the first question, I forgot, what was it?
Oh, okay. Can the MPS identify the quantum critical point and compare versus your experiment?
Okay, so that's a good question. And from the top of, we try to identify the tip of the dome experimentally. I believe that they should be able to estimate what is the highest, the tip of the dome with the MPS. But the problem you see is that, I mean, it's a finite size system. So essentially there is no real divergence. I mean, if you want to know where it is here on this, if I remember correctly, it's about at 2.5. So you see on the staggered magnetization, for example, nothing very wild appears because when you approach the dome, you are kind of the divergence of the correlation length, for example, and you already have a pretty strong fluctuations in the staggered magnetization. And so essentially, it reasonably looks smooth. So I'm not sure that you can completely extract from this where the critical point would be. What we try to do experimentally, and the problem is that it's a very indirect measurement, so we are not really making too much of a big fuss of that, is trying to go back and forth and trying to see where we have non-adiabaticity in order to kind of locate. We've done that. I cannot say that what we obtained was super convincing in terms of fully mapping the dome. So for the moment, as on top of that, the evidence is reasonably indirect, because in order to know where you are, you need to exactly know what is the gap all along this critical line. So.
Okay, great. Thanks for that answer.
A little bit of a related question. You have done these linear ramps. Have you tried to make them kind of smoother, maybe exponential, or a different shape? Have you seen a big difference if you try that? Or does something come out of the calculations that these are better?
So that's an excellent question. So indeed, we've tried various slopes and also various shapes, the basic idea being to be as slow as possible when you cross the quantum phase transition. I would say that we have not seen any wild difference and big improvement in terms of the state we obtain at the end. Therefore, we kind of use this, and at the end of the day, we want it at the same time. It's not only that we are only interested in the final state, the antiferromagnetic ordering, we're also interested in trying to look at the dynamic throughout the thing. So, I mean, in a sense, we haven't pushed that much the shaping of the optimal control, if you wish, of the ramp, so that we cross the phase transition very slowly. But as I said, when we did it, by varying the slope locally, we have not seen a huge difference between the, we haven't seen a huge difference. So, I mean, that's the only thing I can say. I mean, it's not super convincing maybe, but yeah. I'm sure there are ways to do that and to be, you know, you would go there pretty quickly because essentially the gaps are large or in the paramagnetic phase, and you should slow down here. But so varying the slope, we've done that to vary the slope to kind of explore Kibble-Zurek mechanism in this. It's a bit challenging actually to be able to, at the moment, extract something which is meaningful. The exponent that we have, I mean, we can have essentially anything we want. So it's not, so it seems to be reasonably subtle what happens here. So.
Okay, thanks.
Why does it scale that bad with the increasing number of atoms? Because you start with a 6 by 6 of like a super small error of like maybe 1 or 2, and then you end up with a like 3 times the amount of atoms, and an error that it's went like times 10.
Yes. So I mean, here we also have the 4 by 4, 8 by 8, and 14 by 14. They couldn't run the MPS, so we don't have it. I'm not sure I have a super good answer to give you. I mean, for sure, when we grow the size of the array, the big issue we have is that we need, of course, to have the light. So this becomes an important effect. So for example, if I actually go back here, so you see that why do we have this kind of shape in the correlation map? Actually, this is the waste of the excitation laser. You have to see that here, this array is about 100 micrometer. So now if you want to shine the light to create the transverse field, you need this light to be as homogeneous as possible. So to have a waste which is as large as possible, and you know, you have a finite amount of power, so we cannot do that. So essentially what we see here is the profile of the laser beam. So I mean, for sure, when the size of the system grows anyway, we will run into this until we kind of shape the beam in a smarter way. The second thing as well is that when you increase the number of atoms, anyway, the gaps become smaller. And therefore, for a given speed, you will produce more defect, which is to say the staggered configuration, magnetization will be lower. So all these, you know, the good news is that, I mean, so those are all hand-wavy arguments, but I mean, at the end of the day, they all kind of contribute. So it's kind of clear that we are more sensitive for larger arrays to all imperfections on the experiment.
Yeah, thank you.
Are there other questions that? No? So Valentin, should I proceed? Or?
Yeah, I see no more raised hands. I think you can just proceed. Yeah. Thank you.
Okay. So what I would like to discuss next, so there's no Rydberg in what I'm going to say now. It's another experiment where we try to induce, it's again looking at many body physics, but now the interaction is induced by light. So this is really looking at this kind of situation. So essentially the question we ask is reasonably simple. Just take an ensemble of emitters. So we can take a gas. It will be a gas of cold atoms for us, but that could be any ensemble of emitters. And you drive them reasonably close from resonance, and you ask the question, okay, what's going on? What is the amount of light that goes out? I mean, obviously, we kind of know this from classical ENM, but there are actually some kind of subtleties when you start to pack the atoms close to each other. Because what happens in this case is that all the dipoles that are induced by the light, they become large because you sit close to the resonance, and therefore, they not only radiate, but they also interact with each other. So when the medium is dense, and you drive the system close to resonance, then you have to take care about the interactions between the light-induced dipoles. If you want to see what it leads to, but essentially it means that the entire system, instead of being scattering individual atom by individual atoms, you need to consider the scattering of the whole ensemble as a whole, because they are all kind of connected to each other by the interactions. So what we do really, when we look quantum mechanically at the problem, is that the interaction that describes quantum mechanically this dipole-dipole interaction is the resonant dipole-dipole interaction with two level atoms that are resonant. One atom is excited, the other one is in the ground state, and they just exchange their state in a way which exactly implements the spin model I was mentioning at the beginning of the talk. So not the Ising, but the XY or exchange or whatever spin model. You can calculate, it's not an easy calculation, but it's possible to calculate this VDD here, which is the dipole-dipole interaction. It turns out that it gives you exactly the results of classical ENM, where the VDD has a scattering part, 1/r. It has a 1/k r³ part, which is the dipole-dipole interaction, the phase factor due to the propagation, and there is this induction part, intermediate field. The thing which is important here is that you have complex numbers in this quantity. So it means that in certain limit, this Hamiltonian is a non-Hermitian Hamiltonian, and therefore what you are studying really is a dissipative spin model. But the dissipation, which corresponds to the imaginary part of this number, is intrinsically collective, and therefore it's not a trivial Markovian dissipation. What means being dense in this regime? Well, you see that. I mean, here, the typical strength of the interaction is the line width, and it's divided by 1/kr or kr³ or whatever. But it means that if the atoms are closer than 1/k, which is to say λ/2π, then the strength of the interaction becomes larger than the line width of the transition. The consequence of that is that if one atom of the ensemble is excited, it can, of course, radiate in free space at a rate gamma, but it can also, with a larger probability, exchange its state with a nearby atom. And this is, again, the kind of quantum mechanical way of seeing this dipole-dipole interaction. People have looked at that in many different systems, but there was kind of a resurgence over the recent years of these ideas. And experimentally, people have looked at that essentially in random ensembles. So people have looked at that in hot vapors contained in cell, for which it's very easy to get very high density, but you've got Doppler broadening. So, I mean, there are many groups that are looking, I just named a few of them. We have looked in our group and together also with the group of Jean Dalibard at what happens if the system is very dense and very small, typically, so dense colored atoms. And there is a lot of work, really a lot of work that has been dedicated to dilute cloud of cold atoms, but usually which are optically thick. So in MOT with a very with reasonably high density for MOT, but still much dilute than this. Okay, but of course the problem with random ensembles is that you do not benefit from the full strength of the dipole-dipole interaction, and you can see it here. I mean, the dipole-dipole interaction, essentially in order of magnitude, it's given by this phase factor, so the propagations divided by kr, if you look at the far field. And if you take a given atom in the ensemble and look at the contribution of all the others, because of this random phase factor, it's actually a reasonably weak effect that you see. So if you, of course, structure your and pattern your arrangement of dipoles, you will need to enhance by a lot this, the optical response and the influence of the dipole-dipole interaction. So just looking at that in 1D, and there are ways to reach strong control collective effect by structuring the array. So just look in 1D here. There are situations where, for example, all the dipole would point in the same direction. So this leads to subradiance in the sense that the decay rate of this chain of atoms is larger than the single atom decay rate. On the contrary, you can imagine kind of a staggered, it would be a 1D Néel state, if you wish, a staggered configuration of the dipoles, in which case you would lead to subradiance because all the fields interfering would be opposite in phase and therefore would cancel. People have looked at that, and there are many names that I put here, and I cannot even cite the work. There are really a lot of work, and there are a lot of very nice work done by Susan and Misha actually on this. The figure I show is from a paper of Derek Chang, but essentially the idea is that in one dimension, if you bring the atoms closer than λ/2, 1/2 of the wavelength, then you reach a point where you have many of these subradiant states. And actually, what those subradiance means is that it's kind of a photonic band gap effect, if you wish, that the light is guided through the chain of atoms. And the only possibility for the light to escape is through the end mode. There is, I mean, what was the motivation of that? I mean, because you can kind of tailor those interactions and hopefully realize enhance atom-light interfaces, optimize clocks, can look at topology in dissipative context, hope to see nonlinear optics, like the medium is actually a nonlinear medium induced by the interactions. And there was some recent experiment done early this year in the group of Emmanuel Bloch, where essentially they use one array of atoms in a mode phase, mode insulator phase, and they looked at that as a mirror, which is equivalent to what Misha had done actually a few years ago with his DMD. What's the name of the molecule? I forgot. But this single atom TMC or almost graphene-like structure. But it's kind of the equivalent of this. Okay, so I'm not going to show that we have achieved any of this. I mean, it will be much more basic. But first, we try to look at scattering in a chain of atom, and I will show you how we produce that. So we have updated a second setup that we have in our group in order to now implement two sets of high numerical aperture lengths in a cross configuration. And with that, we can observe the chain along the axis and along the axis, but also transversally and also excite in different directions with high resolution. We do that also, as we've always built in our group, based on asphere lenses. But something that we have introduced is the idea of a tweezer with a tunable waist by adding a tunable lens, which is one of these auto-tune devices. We put a telescope here, and in this way, we can dynamically tune the waist of the laser. And you will see that it's useful. Then we can observe the light on the CCD, and that's it. Okay, so let's just
Antoine, what's the time scale of this tuning?
The tuning is about a millisecond.
Okay, thank you.
Usually, to tell you the truth, we operate more on a 10 millisecond because if you go too fast, this kind of gelatin type of thing, they kind of wobble and it results into oscillations. But yeah, that's the typical time scale. Yeah. So in order to produce a chain, what do? We combine the transverse confinement from the tweezer together with the retroreflection of the tweezer to prepare a one-dimensional array. And in this case, we have this lattice structure, and in each of the traps, we can put an atom, and essentially, because it's transversely confined, you've got a well-defined chain. Of course, there is a bit of fluctuations around the axis, but still it's not too bad. Okay, and the typical distance, of course, is just the wavelength of the light we use divided by 2. And by tuning this waist, we can prepare long or short chains. So that's the fluorescence image taken transversely from the high numerical axis of this chain of atoms. And you can not resolve the sites, and the imaging system is about 2 sites. But essentially, you've got this 1D chain, that fluorescence. And if you make the waist a bit larger, the relay distance is larger, and you've got a longer chain. So typically, in this way, we can fill about 200 sites, half filled, each of them, on a reasonably cold temperature. And so with this, we've tried to look at how the system responds collectively to light. So we do an experiment which is reasonably simple. We just shine the light along along the chain with this random spacing, but by quanta of lambda essentially, and we measure transversally what is the fluorescence. And we can send the light, the excitation laser at 780 nanometer. This is rubidium that we use, either along or transversally. We do that, of course, you need to make sure that the atoms do not move, so we switch off the trap. We have to send probe lights that are very short so that we do not induce any motion or heating. So I mean, this one is a bit delicate. I mean, you need to work to make sure that you do not bias your measurement. But at the end of the day, what we can measure, for example, you just integrate the full fluorescence that you obtain on your CCD camera, and you vary and you measure how much you have as a function of the tuning of the probe. And so depending whether we send the probe perpendicularly to the chain or along, we do see that there is a shift of the line, and this shift is induced by the interaction between the dipole, as I will show you in a minute. One thing we can also do is, as we have the resolution across the chain, we can measure locally what is the spectrum, which is to say, for each of these slices, if you wish, we measure this spectrum and we see whether they are shifted in frequency. And what we observe is that if we send the probe transversally, there is no shift. And if we observe longitudinally, the shift is growing as you move along the chain in the direction of the probe. So what is going on here? I mean, the explanation is reasonably easy, and it's kind of easy to write a model to do that. That was done actually by Robichaud a few years ago. But essentially, as you move along the chain, what you have is a constructive interference, if you are red detuned, of all the fields emitted by the atoms located before the one you are considering. And so you can even do a small model, which equivalent, I mean, and maybe Susan will be happy with that. I mean, it's nothing but the collective length shift in a chain. So essentially, we just add up in a coherent way all the interactions from all the atoms before. And this is a way to have the collective length shift. And essentially, this is what we measure here. So the bottom line of all this is that this structuration in 1D already is a proof that you enhance by a lot the collective response, the optical response, because the atoms are very far from each other. They are separated by more than a lambda, and yet the effect is really visible and measurable. If you had done the same measurement that we did a while ago in our group with just a random distribution of atoms, you would not have seen any shift. The shift would have been extremely small. So really the structuration enhances the strength of the shift. All right. The second thing that I would like to show you in the last 10 minutes is another effect. So I presented you in the introductory slide on this part, this 1D chain, where I say it's a chain, so the chain we have. And I also showed you that if the atoms are close enough, you have subradiance. And so I want to show you subradiance that we obtain, but not on the chain because the atoms are too far to be able to observe that for the moment. But I also want to motivate why we are looking at these subradiant things. And there are lots of ideas around, and including coming from Suzanne and people at ITAMP and Misha, is to use subradiance as the possibility to store light, for example, and use that as a quantum memory. So subradiance is this idea that you have modes with extremely long lifetime. So this is what you want to store the light in a sense. But you need, and there are a few papers, I mean, that predicted that over the last few years. Once again, I named a few of them. But what you need is a medium able to sustain subradiance. You need to have a way to store and to write a subradiant excitation, and also a way to release the excitation. I'm not going to show you how a smart way to store. I will show you how we prepare the subradiant excitation, but it's not particularly smart. I will show you how we observe that and a way to release the subradiance. Before I do that, maybe just so that we are all on the same line about what is this subradiant thing, let me just briefly remind you that if you have two atoms that are coupled by these dipole-dipole interactions, you essentially have two eigenstates, two eigenmodes. They correspond to the symmetric and antisymmetric combination of the two states. One has a very long lifetime when the atoms get close to each other. The other one has a very large lifetime, twice the lifetime. One is the subradiant mode, the other one is the superradiant mode. So this is a mode with long lifetime, so essentially a very small decay rate. The imaginary part of this coefficient that I showed you earlier is actually the decay rate. Of course, this is just for two atoms. You want to extend this idea to many atoms, so let's just consider this random ensemble. You can view it as one particular dipole being coupled to all the other dipoles by the fact that the scatter field that radiates on the particular dipole you consider. And therefore, you have a linear system which you can diagonalize, and that gives you modes. So the modes corresponds to given phases between the different dipoles. And you can plot the various eigenenergies and eigen widths, if you wish, of each of these modes. you find this kind of graph. So in abscess, this is the energy of the mode, the E alpha, if you wish, with respect to the bare frequency. And here, this is the width of the mode. So what you have are all the modes that are above, that are line width above the natural line width gamma of the atom are called superradiant. The other ones are called subradiant. And you see that there are many of these subradiant states for the kind of ensemble that I consider here, which is about 300 atoms located in this volume. Okay, so subradiance has already been observed in different systems in recent years, but in the context of cold atoms, it was essentially observed by the group of Romain Kaiser and William Guérin in Nice 4 years ago. The idea was to take a magneto-optical trap, which is very large, many atoms to be optically dense. And they send the light and they measure the decay of the light after they switch off the excitation. And what they measure is non-exponential decay of the fluorescence. And the non-exponential decay with the appearance of very long tail is the signature of subradiance. They have to be very careful to make sure it's not radiation trapping and so on, but they've done that. And at the end of the day, the two findings that they had is that the subradiant time is proportional to the optical density of the cloud. So this is one important feature for this large ensemble. And essentially, they could explain, not quantitatively, but at least qualitatively, everything taking this scalar approximation. The atoms are very far from each other. You just take these terms. In our case, I will show you another regime where the cloud is denser, much denser, and is also of a size which is smaller than the wavelength of light. And the question is, do you still can you still have subradiance? Because now you have all these terms, 1/r cube and all this. I mean, does it break or do not break the subradiance? And the second important question is, of course, it cannot be governed if the ensemble is smaller than the optical depth just by the, if the ensemble is smaller than the wavelength, it cannot be governed by any quantity depending on the size, because the sample is smaller than the wavelength. So essentially, you will only be sensitive to the total number of particles you have. So this is how we do the experiment. So we try to use our tunable lenses to compress the trap. We can trap in a tweezer of about 2 micrometers waist, about 5,000 atoms. They are extremely hot, but it doesn't really matter for what we want to do. And they're also extremely dense. So typically, 10 to the 15 atom per cubic centimeter, which means that actually they are extremely short-lived, typically a few milliseconds. But it means that we have a density such that within a wavelength divided by 2 pi, we have 1 atom. So it's a dense regime. And so this is the experiment that we do. So we start from this. We send a probe, which for this was linearly polarized, still on the D2 transition of rubidium, send short pulses, and we measure the light that comes out after the switching of the light. We drive the system very strongly in this case for reason I'm not going to explain too much. If you have small number of atoms, this is what the fluorescence looks like. It decays linearly as you expect, and you can simulate that by the optical Bloch equations for independent atoms. Nothing special occurs. What you have here, and that's very important, is the pulse that needs to be switched kind of rapidly, and you need to make sure that it doesn't drive the system while you switch on. Now you increase the number of atoms in the trap all the way up to 5,000. And you do see now, first, superradiance at the beginning, and second, you do see the appearance of this very long tail, which is the signature of subradiance. So we try to characterize that. And so, for example, what we've done, we measure this decay rate at the end as a function of various parameters. And so, for example, you try to keep constant the density, but you vary the number of atoms, or you crank up the density by a factor 2. So it means taking a volume which is twice smaller, or you just do the measurement at the same density, but just at the same atom number, changing the density, and you plot for all of them the decay as a function of the optical density. It could be the density as well, doesn't matter. You plot it as a function of a quantity which depends on the system size. And what you find is that essentially there is no universal law. But now, if you rescale everything and plot it as a function of the number of atoms, all these curves now collapse on a single curve. So this is really the signature that indeed, for this small volume, which is smaller than the wavelength, essentially the size doesn't matter. So the relevant parameters that governs the subradiant time is the number of atoms. We've also looked in detail at the influence of the detuning of the excitation, of the strength of the intensity that drives the system. And essentially, we found that this Subradiance time is independent of that. Okay. So that's kind of the characterization in this kind of new regime of the Subradiance. And so now let's go back to this idea of being able to store an excitation, a Subradiant excitation in this. So what I'm going to show you is the stupidest idea in order to do that. So I don't claim anything smart. You just prepare initially, you excite your system. So you're going to excite many modes, superradiant modes, subradiant modes. And essentially at the beginning, you've got in the strong drive some kind of statistical mixture of all these modes. As time goes on, of course, all these modes will decay, but with a decay rate which is different for each mode. The subradiant will decay faster, the superradiant will decay faster than the subradiant. And after some point, if you wait long enough, of course, it's still decaying, but you are left with the only modes left, which are the subradiant modes. So this is one way to place subradiant excitation in the cloud, if you wish. But now what you would like to do is that at some point you want to have this excitation that comes out of the cloud. So the way to do that is to think of it in this way. Subradiance results from the coherent coupling due to the resonant dipole interaction. That's what leads to these collective modes, subradiant with a decay, which is gamma subradiant. But now, if you want to release that and make all the atoms independent, just randomly switch or detune all the atoms with respect to each other. In this way, the interaction is no longer going to be resonant, and therefore you should be back to a collection of independent emitters, and the light should come out at the lifetime of the single atom. How can you do that on the experiment? Well, I mean, you would just use the dipole trap. If you switch the dipole trap back on, the atoms not being exactly at the same position in the trap will see a light shift, which is different from atom to atom. And that's exactly what you need to have a random detuning atom by atom. So another way to look at that is that if you measure the distribution of decay time without the dipole trap, you've got this kind of broad distribution. So included those pretty long state, which are the subradiant state. And now if you bring the trap off, actually you kill the coupling and you are back to essentially the lifetime of a single atom. And so you can do a numerical simulation to see what's going to happen. So assume that you are within this decay and at some point you turn the trap back on, you should expect that the system is going to decay back at a speed or a rate which is given by the single atom state. So
wait,
let's do that. Sure.
So something got.
Yes.
Could you go back? Sorry, a wire got crossed in my head. Could you go back? So, sorry. So here you're saying with the trap off.
Yes. When we do the expression that I showed before, remember the sequence. The sequence was we do everything when the trap is off. So all the atoms have exactly the same detuning. So the coupling, the dipole-dipole coupling is resonant in this case.
So isn't that when you get your subradiant behavior?
The subradiant behavior, in a sense here, you got it here.
When the trap is off, right?
When the trap is off, yes.
So in your histogram, why is it, in your histogram, it looks like the opposite or no?
So probably, I
think the labels are missed.
So the broad distribution means that you've got many modes with different eigenfrequencies. That's the reason why it's broad. You've got modes that are superradiant, subradiant. Now, so that's when the trap, I'm sorry, okay, I got it. It's because the labels are wrong. This is off, this is on. Sorry about that.
No, totally fine. It means I'm following, so I'm good. Thank you.
Thanks for pointing that out. All right. So that's what we do on the experiment. The very same curve as before. At some point, you switch the trap back on, and indeed, you see this increase of fluorescence in the direction of observation, and the atom starts. So this dotted line here was the subradiant lifetime, and you do see that now the atoms release the energy at a rate which is much faster. And it's essentially, it's not quite because we are not completely killing the coupling, but it's like 1.5 times the lifetime of a single atom. And you can vary the time at which you do that, and each time you do find that indeed you can release the excitation. So I'm not claiming that this is something super smart. I'm just saying, well, this is just a way to illustrate how you can recover a long-lived excitation in the system by patterning the detuning on each of the atoms, and we have kind of an easy way to do that with the dipole trap. Okay, there is something we don't quite understand yet, which is it seems to be that the release is also directional, because if we measure either along the axis or transversally, we do not recover the subradiance the same way. So, but this is still something we are not quite sure of. So I was discussing that a minute ago with a colleague, so should not discuss that too much. Just to finish off on this part, and actually I've been quite long, so what's the outlook and what are we looking at? So we are looking also at the other part, which is what happens shortly after switching of the trap, and we do observe superradiance in this thing. One very important question we want to look at is what is the statistics of the light that comes out? Is it classical light? Is it non-classical light? Because I mean, this is a medium with strong interactions between the particles. It should have some influence on the light that comes out of this system. And there are also some interesting questions to look at. I mean, if you look at 1D sublambda array, for example, people have suggested that the correlation between the spin excitation, so the excitation of the atoms, should kind of look like a Pauli exclusion blockade issue. So that's something we would like to look at. I mean, it's how you correlate the excitation in the system and what it results in onto the light. But for this, we need to structure the sample in 1D with a less than lambda over 2, and at the moment, we are not there yet. Okay, but so this is what we're working on this other project, which is not the Rydberg project. So now is really the end, sorry. The conclusion, so I showed you two examples of what you can do with these arrays of atoms coupled to the dipole-dipole interaction. So exploring many-body physics in situations that starts to be non-trivial and challenging for the theorist. And also that, so this is with the Rydberg platform, which operates in a coherent regime in a sense. And then we also have the possibility to play with optical dipoles in order to look at a new type of atom-light interface, non-linearities. And yeah, and that's it. So thank you very much for your attention, and sorry for having taken so much time. So.
Thank you so much for this very nice talk. I'm sure there'll be more questions.
Can I ask a brief one? Sorry, I need to run off, and I have a lot of questions regarding your last part, but just a clarifying question to start with. I will probably contact you later on again about that. So with this optical depth question, this is of course also a question from which side you look. So where you say that it's not optical depth dependent, is it in the transverse or in the axial direction?
Okay, that's a very fair question. Essentially, I try to give an intuition of why we believe that in our regime, it's more dominant, that it's more, the number of atoms is more relevant than the depth. You're completely right that experimentally, we are not completely in this ideal regime of a sublambda. It's sublambda for one direction and not for the other one. So I'm not saying more than that. And once again, it's an experimental finding that what seems to govern the subradiance is the number of atoms. How can we understand it? You can do simulations, it will confirm this, but one way to understand it is that essentially when you become on the size of the wavelength of light, essentially the optical depths can, or any quantities that depends on the size cannot be relevant. Now you have to be careful with the optical depth not to forget also all the 6 pi over k square and all this crap, because it can easily be give you the factor that you're actually wondering with, because indeed along one dimension we are not subwavelength.
Yeah. Thanks.
So maybe regarding the initial conditions, like when you illuminate the sample, how many of the atoms do you actually excite, or does it depend on that?
Okay, so that's one thing I haven't emphasized too much. When we operate there, we do I over I sat, which is 30, and we've pushed even all the way up to 100. So we do believe that essentially half the atoms are excited.
Okay, but the saturation value would be for non-interacting atoms, right?
That would be for non-interacting indeed. But I mean, if you are at 100 of I over I sat, you start to overcome and to power broaden the system by a lot. So our belief, but once again, actually this would be a question for you guys in theory to calculate that. What we believe is the initial state here is kind of a tensor product of, 1/2 density matrix for each of the atoms. That would be reasonable ansatz to describe the initial state that we start from. An experiment that I'm very interested in doing, it would be, because of course, if you start with 1/2 and 1/2, in a sense, indeed, what I've written here is kind of true. If you decompose, you will have a superposition of Subradian and Subradian mode. But for example, what happens if now you fully invert the system? Then there is no initial coherence created at all. You never have cross terms. You only have E. Will you build a subradiance as you decay? And to tell you the truth, I am not entirely sure. So we are, the point is that experimentally it's super challenging to do this experiment because you need to invert systems. So you need to have a lot of light on a short amount of time. And we just have mundane problem of experimentalists that you cannot switch off the light fast enough, blah, 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 not to drive the system even in the Subradiance state. So it's a bit technical issues, but they're actually annoying for these studies. But you see, I mean, the initial state was, I don't know how important it is. This state, if it's 1/2 for each atom, the density matrix to the power n, indeed it can be decomposed as I've written here on matrix density, matrix associated to Subradiance state. But if you start from a fully excited system, you do not have this any longer. Yeah. So this idea of filtering through the decay is not necessarily the good idea.
You also like turn around this idea with switching on and off the trap, like for storage. Can that somehow be done so that you somehow
to switch it on? Sorry,
I mean, like you switch on the I mean, you switch on the.
That's actually, that would be the dream, but at the moment, the level of control we have is not enough because you would need to so in a chain which you would resolve. Sure, I mean, you could, for example, assume that you have a chain, which is, let's say, λ/2 spacing, and you imprint with a laser a phase pattern, which is also π/2. So in this way, you couple maximally to this. You see, when you do the excitation, because the phase in your excitation laser has the phase of the modes you want to excite. Here, it's totally not controlled, this thing. Yeah? So we most likely, I mean, we do not have too bad an overlap with Subradian modes, because otherwise we would not excite anything. But it's far from being ideal. And as you see, Subradiance starts to develop at 10⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ subradiant modes.
So, sorry, Alex, were you going to go? Go ahead. Go ahead.
I actually have a question that is basically this last point that you said. So if I understand correctly, you're doing a fit to your decay to say anything about the subradiant mode, and it seems like you're treating it as a single thing. But can you say anything about how many different subradiant modes you have, or anything about them based on the intersect of this fit on the particular time scale that you observe? Like, can you extract more information than just saying it's a slower decay?
Yes, we can, but we are doing that. So I don't want to say things that may change too widely. But indeed, you're completely right. I mean, you are in the strong driving. I mean, let's even assume you are in the weak driving limit. You have 5,000 atoms for this experiment. It essentially means 5,000 modes. Okay, so it's clear that when we are here, we still have a lot of modes that contributes. But it's just that if you go back to what I showed here, it turns out that many of these modes essentially have the same lifetime. So that's the reason why in the fit, it hardly shows up as, you know, still many exponential, but it looks pretty much like one exponential. We are trying indeed to infer what is the amount of subradiant modes that we have excited in this. It's a bit complicated because the excitation is in the strong interaction, in the strong intensity regime. So I'm not quite sure of how we can push that, but we're trying to do that. So it's a very fair point to have.
I have a kind of follow-up question, and I know that this is going to be very hard because what I'm thinking about is that right now you're dealing with like random distributions of atoms, right? So every time you run the experiment, you're doing something slightly different. But if you turn on the trap, then you kill this resonance condition, and then you go back to your usual kind of decay. But if you turn it on, another way of interpreting this is that as you have a position-dependent light shift that is actually introducing some phase evolution.
Exactly.
If you turn it on and then back off, you should have mixed your subradiant modes into a combination again of subradiant, superradiant, and so on. Can you do such a pulsed experiment where you can actually infer more than what you have currently?
That's a very good idea, and that's actually exactly, it's funny that you're mentioning that, but we are discussing that this afternoon. So that's certainly one experiment we would like to do. Because indeed, you're right. I mean, imposing the light shift means there is a time evolution of the full state we have, and therefore we should be able to, I mean, by tweaking the time in the right way to add mixed superradiance, for example. Yes.
Related to that, actually, first off, I thought this was all super cool. Thank you so much for the talk. Secondly, I think this probably doesn't work out because of the fast decay timescale, but is there any interesting connection to some sort of like localization physics? I mean, forgetting for a second that it's like in 3D, but the fact that you're introducing this kind of, you have this like XY model, and then you're introducing this disorder in the energy. Maybe I get that it's a bummer because it just decays away so fast, but maybe, as Alex says, if you kind of imprint random phases or something, you can recover this type of localization physics.
Yeah, well, I know that some people are trying to look at this subradiance problem in terms of localization. I mean, this is something that Roman Kaiser in Nice does a lot. I'm not sure I would be able to tell you anything smart. So apart from people are trying. So, and indeed, I mean, you have the ingredients. This is what you're saying. You have the XY model. You have random coupling. So, I mean, this is a good start. It's a dissipative system, though. So it's not exactly in the same framework as MBL, for example, which essentially is just removing dissipation from the system and looking at the memory of the initial state. I don't know. It's yeah. Yeah, I don't know. I don't know what to answer smart apart from the fact, yes, people are looking at connection, but I don't have anything in intelligence to say. So.
Hi, sorry. I may have a very naive question because you mentioned at the beginning, like the motivation to study this subradiant thing is to use this as a quantum memory. Could you elaborate a little bit more about how this could be used as a quantum memory and what is the kind of the information you stored here? Is valuable or something else?
Well, at the moment, the only thing we're storing is an information. It's just an excitation. So I haven't said anything about what happens if I send entangled photons in these things. What am I going to store? I have no idea, to tell you the truth. But of course, this is the interesting question. If you want to claim that this is a quantum memory, I'm not even sure, to tell you the truth. I haven't read for example, the Direction paper very recently, so I do not remember all the details. I don't believe that they do more than photon storage. So, you know, in a sense, I don't think that they are claiming even that it's a quantum memory. This is towards, but that's a very fair question. So maybe I should not have called it a quantum memory because this is pushing way too far. So,
thank you.
So it's a delay line if you wish, but I mean, it's very complicated delay line, but
yeah. But it's also kind of conditioned delay line, right? Most are not delayed, partially delayed. So, yeah. Thank you.
Thank you.
I have just a technical question. How do you get such a good resolution on the decay rate? Like at which point do you receive each photons? Because like the scale is like nanoseconds.
Yes, so we use avalanche photodiode, so single photon counter. So the resolution is essentially limited by the jitter of the photon counter, which is 150 picosecond. And so all this data, there have been, I don't remember if it's 1 or 4, it's 1 nanosecond, yes, the beginning. So
okay, so
this is an histogram that we plot. So it looks like a line, but essentially for you count the number of photons you have.
But so those things, you can sort of trigger them at 1 nanosecond precision.
No, they trigger on their own. So you switch off the trap. So it's a TTL signal that says, okay, trap off. And then it's a start-stop measurement. You stop when you have a photon which arrives, and you can. And it gives you for this particular time. You and you build the histogram from this. Okay. Yeah, sorry. Maybe I should. I mean, I agree with you. I mean, if you haven't thought about that, usually it's a bit confusing the first time you do it. But I mean, this is usually wait time.
Especially because I had in mind the schematic where you had like EMCCD camera, and I was like, oh, that I don't understand how you do that.
Right, I should have said that. It's a very fair point. We do, of course, this measurement with avalanche photodiode. It's not with the MCCD I mentioned before for this particular experiment. Yes. Yes. So it's things to change on the slide. Anyway.
Okay. Is there another urgent question? Seem to be the case. So thanks again, Antoine, for this very nice talk, very pedagogical, and for taking the time to answer all the questions. Very nice, lively discussion.
As usual, pretty impressive sets of questions. So now we've got a
yeah, that's
very much to you all. So all right.
So yes, thanks again. So next week is Thanksgiving, so we will have no talk. And then the week after, we're coming back with Ana Asenjo